Great. So hello, everyone. I want to welcome you to the second in our HBCD EEG lunch lecture series for those of you on the East Coast. It's my pleasure to introduce today Dr. Makoto Miyakoshi, who is going to be talking to us about EEG processing. And Makoto said that he's willing to take questions during the talk. So what's the best way for us to do that, Makoto? Should people just raise their hands or just say something to you?
Yeah, say something.
Okay, so if you have a question, Makoto is willing to entertain it during the talk. So please feel free to do that. Okay, Makoto, the floor is yours.
Thanks. Let me share my screen. And let me see. Well, let me see. How does it work? Let me try this.
There you go.
Okay.
Yeah, perfect.
Oh, good. Thanks. Hello, everybody. I am Makoto Miyakoshi. I am an assistant professor at Cincinnati Children's Hospital. So today I'm going to talk about the pre-processing of EEG data. When we talk about the pre-processing, of course, the first question is why do we even need to do that? And the answer is obvious. That's because what we call EEG signal contains various other kinds of signals than pure brain signals. So let me start with this history because history is always fun. So this is Hans Berger. He is the first mankind who reported the scalp recorded like non-invasive EEG in 1929. But the interesting fact is that he made the first observation of the EEG in 1924. So he spent 5 years wondering if he should publish it or not. That's precisely because he also knew that there are a lot of other kinds of the artifacts in his data. So it was a dilemma for him. He knew the value of his potential findings, but at the same time, there is a huge risk of publishing something completely nonsensical. So in order to publish his first paper, he conducted 174 sessions and he made 866 measurements, which is a really large number, right? And at the point of 1928, which is 1 year before his first publication, in his diary, he says, "Oh my gosh, I totally wasted my time. I shouldn't have done anything about this EEG because this is completely bogus." So he was really oscillating between those confident states and losing the confidence at all. So in his first paper, spending almost more than 20% of the volume, he argued the various types of the artifacts, which is listed here. And this concern is still valid for today's EEG research. And the persistent skepticism about the brain origin-ness of the EEG continued more than we usually think. This is a 1970 paper, which is almost 40 years after the Berger's first publication about the finding of the non-invasive scalp EEG. This professor from UC London, I think, said that this EEG alpha, what you call, is actually not brain origin. He said this is actually from the eyes. And this was the 70s. And much later, in like 1987, there was a the final definitive proof that EEG signal is from the brain. Of course, at this time, by this time, there are a bunch of EEG papers. So maybe it was not really necessary, but according to one of the big books I've read, this is the final proof. So what they did was they used this animal, dog, and they isolated the brain, but not like physically isolated. I think still in vivo situation, but maybe some connections are cut. And in order to remove the eye artifact, they removed the eyes. And in order to remove the heart artifact, they stopped the heart. And they even used this artificial heart to eliminate the electric signals from the heart, but still maintaining this perfusion, so that when they turn on the machine, the blood circulates and the EEG is generated. And when they turn off the machine, then of course blood circulation stops. Then that makes the EEG level much lower. So this on and off the heart is something Barger couldn't do when he was doing his time. But after making those experiments, we can finally say that yes, EEG signal is really from the brain. But as I said, it does not necessarily guarantee the optimism we may enjoy. For example, this is a 2007 paper, and what they did in this study is that they used a special type of the anesthesia that works only for this upper body. So the subject loses the controls and muscle in the face and probably the large part of the upper limbs. But the point is, subject can still use the fingers to make responses. And the subject is also fully awake, and this paralysis does not affect the subject's consciousness and the cognitive abilities. So subject basically performs the cognitive task while only using this fingertip, and everything else in the upper body at least is completely paralyzed. So this with paralysis, I mean the anesthesia, they recorded the power spectrum density that looks like B, trace B. There are 4 lines in B because there are 4 types of the cognitive tasks, but these task differences don't matter at this point. And this trace is A, this is without the anesthesia. So what we can tell from here is that we think we can analyze beta gamma range, but this is kind of the ground truth that how much muscle contribution is still there when we analyze beta and gamma. And in the right plot, you see the exponentially rising traces, and this is basically the difference between with and without using the anesthesia when doing the same task. And so basically this is the amount of the contribution by muscle, right? And it's exponentially increasing towards the higher frequencies. So it's very obvious that without the muscle contribution, the 1/f-ness of the EEG power spectrum density is very clear, right? And with the muscle contribution, it kind of reaches to the floor, which is rather flat towards the higher frequencies. So this is always happens, and everybody's our data contains this muscle contribution all the time, so that we have to remember all the time, right? Another paper I like to cite here in this context is this Yuval Greenberg 2007. This paper was published from Neuron, which is a very high profile journal. So the context of this paper was that at that time, everybody, I mean the EEG researchers are very interested in performing the gamma band analysis, because there are interesting theories like, oh, gamma band is must be related to the binding, like brain's binding function, stuff like that. But this Yuval Greenberg showed that this gamma oscillation is basically Saccade. This is from the eyes. Remember this guy from the 1970s, that professor said, no, this is from eyes, which was refuted later. But Yuval Greenberg, he showed that, probably most of the cognitive, laboratory experiment using humans, if you see something like this, so this looks very much like, this gamma band oscillation seems to be related to how this car image is chopped up. If this is flipped, then even stronger gamma. So let's suggest as if this is a cognitive process. But actually, he showed that when he used this eye tracker, then this high frequency oscillation was observed at the moment of the Saccade. And when he separated the trials into with and without Saccades, then this gamma band activity disappeared when there was no Saccade. So this kind of shocking result periodically appears in our field. So we have to always remember that there was this case, there was that case, because that is only effective countermeasure we can take. So we should learn from history, really. This is much less established, but could be of interest in this context. Now, the left-hand panel, you see the recent Nature Neuroscience publication from the UCSD. The PI, the Brad Wojtek, was sitting in upstairs of my office when I was in the UCSD last year. What they did was, they developed some interesting method to decompose the power spectrum density into this exponential curve and basically the alpha peak. So you fit the curve like this, and you subtract this exponent, and you got the flattened power spectrum density with big alpha peak, which you can also fit the Gaussian distribution. So this approach makes an assumption that this exponential 1/f curve can be fit, right? And when I discussed this paper with one of my mentors in San Diego, Paul Nunez, he said something quite unexpected. He said, it doesn't have to be 1/f, and actually he does not believe that this power spectrum density contains 1/f, at least not all the time. And I was so puzzled, and I asked him why, and he brought his book, and he showed me those figures, and he said, look, do you think these are following 1/f? And we have to pay close attention to the unit, okay? So here, the Wojtek's paper uses log scale. So, you see this curve kind of more exaggerated. And in this plot, these plots, it's a square root of the power. So this is basically the microvolt and not the microvolt square. So this exponent is less exaggerated here. So if you convert it to the log scale, then this is even flatter. So it's much less flatter than these plots. And I asked him, okay, I see your data is not following the 1/f, but what do you think is the reason for this? And his explanation was very shocking to me. He said, because when I recorded these data, I watched all the subjects, and every subject very closely. I watched them, and even if they make the slightest body movement, I said, don't move. And he recorded the data in that way. So he knew that the data he recorded is completely, as ideal as possible. Super perfectionistically, those data were, each data point were recorded from the subjects. And he said, probably me, are using the data recorded in the hospital, and sometimes, yeah, it's from hospital, but many times, because I'm a psychologist, my data sets were from the cognitive experiment labs, like psychologist labs. And you don't watch those data collection very closely. That's why you miss the body movement, and that's apparently those body movement contributes to the lower frequencies, and which is probably why you see a nice 1/f curve. So this kind of how much we care for the artifact really is a fundamental issue. So that's why. And I talk about these things first because these artifacts may or may not be treated in a later signal processing. So there are things we can do and we cannot do in signal processing, right? So someone said garbage in, garbage out. So, but when we take this garbage first, then we might even take it into the basis of how we see the data. For example, 1/f in the power spectrum density is the natural property of the EEG signal, but is that really so? This is a really fundamental question, right? So we have to remember this. Now, let me quickly go to the next step, which is what we can do, EEG preprocessing. So this is typically how we see the data. When we see this, high amplitude burst in our time series presentations, and we think, oh, this is the, this part needs to be removed. Like we see it as if rotten, damaged part of an apple. So that can be cut out to clean the data. So this is like the step one of data preprocessing, and usually this method is effective enough. But here we have to also remember this fundamental fact. So let me talk about it. In the upper row, I see how the ground truth of the MRI signal is collected and relates to the ground truth and its representation in data. So let's say this phantom we call, the phantom is defined in this way, in this triangle, and we scan it in an MRI scanner. And in your console or MATLAB, you see this reconstructed ground truth. So because we know that this reconstructed ground truth corresponds to this ground truth we used, when we find something in a figure here, then we can safely assume that, oh, okay, there was something also in this ground truth, like chipping or something, right? So this ground truth correspondence in the case of MRI is very clear. It's very straightforward. You can also perform the MR microscopy, which means if you increase the resolution of the MRI, like 0.1 millimeter or something, you can still get the image. Of course, it takes time to take the scan, but you can do this. Can we do the EEG microscopy? No. There is a special Nyquist of the spatial resolution of EEG and stuff. So the fundamental question, the problem of the EEG is that there is no such a thing as the ground truth of EEG, which is experimentally available. Of course, there is the ground truth of the EEG, which is the activation of those neurons and synapses and stuff. But those are distributed and it's regulated in a very complicated, chaotic way. So we cannot assume the simple linear assumption between the ground truth and the recorded signal. So I used to say that, because our ground truth in the EEG is so complicated and inscrutable, we generate as colorful figures as possible to escape from the fact that we don't have clear ground truth. So this is probably our effort to escape from the ground truth. We try not to remember the ground truth problem. So this is also very fundamental limitation of the EEG, which we have to always remember. Okay. I'll skip this actually. Here is a Socratic question of, okay, when we clean the EEG, then we have to know what the clean EEG is, right? But can we mathematically or engineering wise, define the properties of the clean EEG? So there are some of these established criteria. For example, the stationarity is a good concept. So stationarity, its explanation, technical definition could be pretty complicated, but simple summary is here. The mean and variance do not change over time. So you set the arbitrary width of window, and using that window, you sample the data from the arbitrary time point, and you take the mean and variance of those sample window. And if those mean and variances are the same across all the random sampled windows, then you can say that your data is stationary. This is like a simple version of the definition. This is also from the Wikipedia figures, and the above plot shows the example of the stationary data, and the data shown in plot below is the example of the non-stationary time series data. So that is a bad signal, and we can, as an EEG researcher, we can agree with this good bad definitions, right? Because in a lower plot, we would say, oh, this looks like Bereitschaft potential that develops over like 2 seconds. So we want to apply a stronger high pass filter or something like that. Intuitively, we can tell that, right? But here is the definition issue. Okay, when we look into the ERP, let's say, starting from 200 milliseconds before and 800 milliseconds after the stimulus onset. Now, is this 1 second ERP stationary or not? And the answer is surprisingly, this is non-stationary, right? Because it starts from the baseline period, which is quiet and centered at 0, and of course it shows the brain's response to the stimulus or whatever this behavioral output. And you see P1, N1, P2, N2, P3. They differ in the latencies and frequencies. So single ERP is non-stationary, which is a bit confusing. But another confusing thing is that, but if you repeat this single trial for, let's say, 100 times, then we can probably say that this data is overall stationary again, because you see these repeating patterns, right? So if you take those random window sampling approach, then you can see, okay, this part and this part are more or less the same, So the definition of the stationarity actually depends on the time scale, right? So that's why it's a bit confusing. It's not like, averaging should be done in this way. No one makes mistake in taking the average because it's so simple and understandable. But the definition of the stationarity, it's like, okay, stationarity in what time scale? Are you talking about the minute, second, or hour, or millisecond? So this is why this concept of the stationarity is not very popular and not very much used in an explicit way in calculation. But stationarity is still a very, very important assumption and the concept in pre-processing EEG. I'm gonna skip these. Okay. The second point is the frequency domain 1/fness. So we have already seen a bit of this, but let me go into that. So let me give you a quiz here, okay? I'm going to show you 2 time series EEG data. This is A, this is B. A, B. My question for you is, which time series looks more like EEG? Is it A or B? And I would say, oh, by the way, this is a 5 seconds, okay? The same, 5 seconds. I would say A contains a lot of high frequency noise because so much spikes, and also the lines seems really flat. Maybe too strong high pass filter was applied or something, but this looks like too noisy to me visually. B, yeah, this is like the balance between this low frequency wiggling and high frequency spikes are more balanced. Although we don't see the cross channel correlation in either of the cases, A and B. That's because these are simulated data anyways. So those differences we saw when we compared A and B can be best explained by this power spectrum density plot. So A is a white noise. White noise is by definition, it contains energy, the same amount of energy across all the frequency ranges. So it's kind of funny to say that EEG, delta, and alpha has the power, and gamma has the same amount of the power. That's like a flat. So if there were such an EEG data, then that should look like the plot A. But almost always, what we see the genuine EEG data, it's closer to the pink noise, which has this 1/f curve. So this Brad Wojtek's lab developed the method called FOOOF, fitting oscillation and 1/f FOOF, in 2020. And this is not only a tool, like a convenient tool to extract EEG features, but it has a pretty interesting physiological assumption and the usefulness in the neuroscience. So let's say there are excitatory and inhibitory input system for the neuron, and excitatory system is controlled by AMPA input, and inhibitory is controlled by GABA. And now first we see the time domain, this spike response of this AMPA and GABA. And it's obvious that AMPA has a sharper spike, right? And GABA has a broader spike. Sharper the spike, when you convert it to the frequency domain, the complete spike has a uniform distribution across the frequency bands. So sharper spike means flatter. And that's the case of the AMPA. And GABA, it has a broader spike. Broader means it has a low frequency, more than high frequencies. So the power spectrum density should show the more exponent. And it's very interesting. They said, therefore, when we see a flatter power spectrum density in our EEG data, that is probably dominated by AMPA. And if we see the exponent that in our EEG power spectrum density, then that may be dominated by GABA. And AMPA dominated, GABA dominated immediately means, excitatory or inhibitory, right? This is very interesting argument, and I like this simplicity a lot. We can take advantage of these known facts, or at least proposed facts. And so, Brad Wojtek's point was the difference between this exponent, but at least we can say that whether it's the excitatory or inhibitory, it follows more or less 1/f, right? And if we see the power spectrum density goes against such a pattern, so for example, this cluster 5, well, this is actually okay, but cluster 6, this looks like a square root sign, and it doesn't follow the 1/f, then we can simply say, oh, because it's not, the power spectrum density does not follow the 1/f pattern, we declare that this is not representing the pure brain signal. It's very simple and convenient criteria we can use. Maybe I'm going to skip this also. So the section summary, 1/fness is always available, and it's pretty reliable, I think. Although we have to remember the skepticism by Paul Nunez. Maybe the lowest end of the power spectrum density is highly contaminated by body movement. And of course, the high part, like the gamma part, is contaminated by the muscle as well. The final thing we can talk about is, when we talk about the signal processing, like pre-processing, we can always follow the established methods, so which may or may not require the declarative knowledge of anatomy or the neuroscience per se. So again, we are back to this figure, and now let's do something we can do. The first choice would be to select this window and what we call reject. So that means you select this window and reject, and you stitch the before and after this rejection. So there is discontinuity there, right, after removing this window. And not many people talk about this effect of the discontinuity, so I run some simulation for this presentation. And top row, this is the intact signal, like simulated signal I generated for this. This is a 4 Hertz oscillation for 30 seconds. And in the top row, you see the time domain representation. And in the bottom, you see the time frequency domain. Now, I rejected, let's say, 15 windows out of that the continuous signal, and that introduced the 30 windows to introduce 30 discontinuities. In order to make the fair comparison, I kept the data lengths the same. So you can imagine that this data was actually 40 seconds, and I rejected 10 seconds of it to make it 30 seconds. So now you see those discontinuities here, right? And how that affect on the time frequency representation. And it looks like this. And you can see sometimes this the central power goes down below 4 Hertz. That's because this McDonald's-like shape is more like big, one big oscillation with a lower frequency. Or sometimes this power goes up because this discontinuity created a sharper spikes. And either this central power goes up or down, every time this discontinuity happens, you see this, the conical shape power goes up to the higher frequencies. That is because this spike, the very, very fine spike, contains a lot of the harmonics. And harmonics is the collection of the higher frequencies. So you see those the conical shape everywhere. What's so interesting to me is that sometimes, depending on how this discontinuity is defined, you completely lose the power at all. And this is pretty interesting to observe this. So anyways, of course, these standard like filter functions, let's say in EEG lab, is designed so that they do not go over this discontinuity, but every time this discontinuity is detected, then this filter function stops before, when the right edge touches this discontinuity, and it resumes the process from the left edge touching from that discontinuity, so that this discontinuity is not included in the final result. So from the user's viewpoint, because this is, this process is taken care of under the hood, so maybe it's not very obvious. But from the analyst, like this, processing viewpoint, introducing, a lot of this discontinuity is makes the process very messy, and also it reduces some sensitivity of the analysis. And of course, the power spectrum density comparison shows the effect of those discontinuities. So this time window rejection, although it seems simple and cannot go wrong, it can actually go wrong depending on what kind of analysis you want to do after. So that's why, and also it's, it requires your eyes and hands to go over. So that's a problem. So, there is a signal processing I can recommend to perform this window rejection. So this is another simulation data, but this is the real data published 20 years ago. So this is EEG Lab's tutorial data, 32 channels and some subject performing the visual attention task. And there are 80 trials of 3-second epochs. Okay. On the left-hand side, I'm showing the original data. So this is a beautiful ERP from the 32 channels butterfly plot. On the right-hand side, you see a whole bunch of positive spikes everywhere between 200 to 800 millisecond range that is added in this way. So in this simulation, for every trial, okay, every epoch, I added 2000 microvolt spike in a randomly selected channel and randomly selected latency between -200 to positive 800 milliseconds. The whole point of doing this is that when you perform the standard epoch rejection procedure after adding this artifact in this way, the remaining number of the usable remaining trial is 0. Of course, that's because every epoch contains at least one 2000 microvolt spike in one of the channels, right? So you cannot escape from that. Then here is our solution. So this solution is called ASR, Artifact Subspace Reconstruction. And you see 8 and 12 and 14 and 20. These are the threshold. So 20 is the most gentle here, and ASR 8 is most stringent and aggressive. And you see these spikes nicely start to disappear, and maybe, but in ASR 12, you still see the spike here. So maybe the balancing point is either ASR 8 or 10. But if you pay close attention to this peak amplitude, this, when you use ASR 8, it's probably less than 30. Although when you use the gentle correction, you have something like 35-ish. So you clean those data, artifact, at the cost of the genuine signal. Of course, this is a trade-off like that. So you can also use a hybrid approach, which is ASR 20, which is the most gentle correction together with the epoch rejection. Then you don't lose the amplitude very much. You still maintain 35-ish peak amplitude, and of course you lose number of the trials, so your signal to noise ratio is a bit lower, but you can still continue your research, right? So this is very good solution, and much better than nothing. There is I can explain this technical aspect of the ASR, but I'm not gonna go into that now because I'm running out of time. But one thing I want to mention here is that even though ASR is known to be, like dependent on principal component analysis, it's not the simple sliding window PCA rejection, because PCA is a part of ASR, which is y equals to v transpose x here. But the final the mixing matrix is here, which is actually the learned from the clean part of the data itself. So it's not PCA per se, but it's a mixture of PCA with the help of the clean part of the input data itself. So that's why it's kind of smart. And if you see this contaminated data by your eye, it's kind of, you know what you want to do, which is I want to break off this spine, and I want to do some minimal makeup for that hole, and that's it, right? That's what we need. That's the minimum invasive approach, but we know it doesn't hurt because we know the duration of this spike is only like 1 frame, like 4 milliseconds, so it shouldn't matter, right? And what ASR does is very close to what you're thinking now. What it does is, it uses a very narrow sliding window of half a second, and it performs the channel-wise interpolation. And of course, this interpolation pattern differ from window to window. So it has that flexibility. And again, as I said, ASR also uses the learned data, which is learned from the clean part of the data itself. So when it performs the interpolation, it's not only using the surrounding channels data, but also surrounding channel data is rotated in a special way so that the result resembles the clean part of the input data itself. So it has such flexibility and adaptivity to each input data, like subject by like individualized interpolation, let's say. I'll skip that. Okay, so that's the section summary is that this continuous data cleaning method called ASR could be an alternative to the conventional window rejection. And Cincinnati Children's Hospital has been working on this project to evaluate whether we can automatize this EEG cleaning process or not, basically using these techniques. Okay, the final conclusion is that EEG is most reliable in mid-range, which is theta, alpha, and probably low beta. And when we talk about very low frequency range as delta or very high frequency range as gamma, then we have to remember those skepticisms and the past publication that shocked all the EEG researchers. Oh, this was not from the brain. Those criticisms are always valid, and we have to be careful. And it's also a good thing to remember the definition of the stationarity. And this is one, although this is not like unitary definition, and there is only one method to evaluate the stationarity, but there are multiple methods to evaluate the stationarity. But stationarity is a good concept to stick to when we talk about preprocessing. And 1/fness, again, with the skepticism by Paul Nunez, generally speaking, if the power spectrum density goes against this 1/f, then that's absolutely not from the brain. So those empirical criteria are always useful. And finally, the ASR, this kind of complicated signal processing may be intimidating because it could look like a complete black box, but you don't need to understand the every mechanism of those black boxes. For example, you can use a smartphone, although you don't know how it works, right? So what we need to do is to understand the input-output relation. And we also have a control. So where those knobs are to tweak. So if you find overcorrection, then how can you reduce the amount of the correction? Or if you see the undercorrection, you want to increase the correction power. As long as you have those controls over your data, then I think that's fine. So those are the pre-processing, my presentation. Okay, thank you very much.
Thanks, Miko.
Thank you. Do you want to stop sharing and we can see if there are any questions?
Sure.
Great. We do have questions.
All right.
Lindsay.
Hi, thank you so much. It was such a fantastic presentation. I love that you showed all the history of this. I think it's so valuable for grounding us. I really, really appreciate that. I had a question about your ASR, and in particular, I'm wondering if the success of the method is going to depend on still somehow figuring out the right parameters for what you're detailing as clean data. So you showed us a simulation where it was obvious what was clean and what was not. That problem of defining clean and not clean gets harder in real data, and even harder with 3-year-olds, 2-year-olds, 1-year-olds. So could you say a little bit more about how you are defining clean data, which ASR then smartly considers in its reconstruction?
Yeah, that's a good question. So I can use this self-referential way to explain how it works. So I said in my presentation, the stationarity, the definition of the stationarity is convenient and also important concept for the preprocessing the EEG data, right? So ASR has a function, like one of the internal functions of the ASR is to evaluate those stationarity parameters. So because ASR cannot use our heuristic decisions, sometimes it's so easy for us to tell, oh, this is good, this is bad. But in order to replicate our human intuition with those parameters, then things start to appear very clunky. But ASR has well, first of all, ASR is not a simple mechanism, but it's a really huge machinery, and you have total of like 31 parameters you can tune. So it's very and those parameters corresponds to the mathematical concepts such as the Gaussian distribution and truncated Gaussian distribution and standard deviation. Those mathematical and statistical concepts are used. And also the key aspect of the ASR, one of the sources of its robustness is that it uses the median statistics instead of the mean, because mean is very weak against the outliers, right? But in the case of the median, you can have up to like 50% of your data filled with artifact, and you can still perform the pretty standard analysis. So if you ask me how reliable ASR is when you have this infants data and there's clinical data sets, it depends on whether this input data contains a genuine EEG signal. And for example, if I find, okay, this input data contains no EEG data at all, then we cannot do anything. And typically, in the case of the ASR, the definition of the good data is not an outliers in the sense of those median statistics. Okay. Of course, it can kick out this flat data as well because the variance is too low. So it targets the good part of this data distribution. And if you go the extremity of this data distribution, of course, you see flat lines here and 2000 microvolt over there. So first you build this data distribution and you look into this central part, which cannot be wrong, at least in the sense of the extreme amplitude outliers. So ASR is actually probably only good at kicking out the high amplitude outliers, and it doesn't do anything fancier than that. It doesn't do anything in the frequency domain. It doesn't do anything about cross frequency something. It doesn't do anything complicated. It's actually very close to what we do when we perform the window rejection. When we do window rejection, usually high amplitude is bad, right? That's the only principle we use. And well, we can actually evaluate the frequency component a little bit, but as we did in the A/B comparison in my demonstration. But usually high amplitude is bad, and that's it. Right? So ASR is outlier rejector in a flexible and smart way.
Elizabeth.
Hi, Makoto. Thank you for such a great talk. That was really helpful. I learned a lot. And I have a little bit of a piggyback on Lindsay's question and then a real practical question. I see that we have a lot of grad students and trainees, EEG techs on the call today, which is wonderful. And so I wondered if you could take kind of a step back and talk about the particular kind of developmental concerns and differences that we may encounter in our HBCD data for the very young kids and how the principles that you talked about relate to that. And then second, for the kind of implementation of this that you're talking about with the stationarity, is this implemented in EEG lab? That's the real kind of nitty gritty. How do we put this into practice with our own data? Thanks.
Okay, your first question, particular things about the developmental data. You know, I moved to this children's hospital just half a year ago, and I'm not that knowledgeable enough to talk about the developmental data, this particular aspect of it. But one thing I can say is that those child developmental studies, often those researchers use the EGI recording system, and there is an EGI issue, I would say. The data quality using EGI, even if you record the adults' data using EGI, the data quality is not very impressive, in my opinion. I haven't run any detailed test yet, but so there are two problems actually. You are using this developmental population and you are using EGI. So those two things are often comorbid. So it's kind of hard to separate for me. I can't tell which is the problem.
Can you, so there's nothing we can do about working with developmental populations. That's what the focus of our work is, starting with very young infants. But I'd like you to spend just a few minutes saying what issues you think are problematical with EGI.
I don't know.
And we won't let EGI know what you.
They don't have enough funds for a hit team just yet. So
Yeah, right, exactly, right.
One hardware engineer told me that EGI does not have a DRL electrode, which is a direct right leg electrode. And usually those modern systems have those DRL electrode. And this DRL is like, it's like another layer of the, the differential recording system for the ground potential.
Yes, that's right. It does not. You're correct that it does not.
Right. And according to his explanation, that's the reason. So I have a couple of data that kind of supports that view, but I'm not myself a hardware engineer, so I can't say for sure. I do like to know as well, but can't.
All right, thank you. Caitlin.
Thanks, Makoto. This was fantastic. I've been part of some conversations lately talking about the reasons for missing this as potentially being important to know. So thinking about, and again, sorry, I'm very much in a clinical population, and developmental population, but we've been talking a lot about how kind of characterizing the reasons for kind of data rejection could even be really helpful. And so I'm curious your thoughts on how well, and I'm in the process of moving more into EEG lab, but I'm curious about kind of how the pipeline kind of accommodates or accounts for the reasons for missingness. And if you think kind of just personally, if it would be more helpful for us in our papers to be characterizing this. So thinking of like, should we be moving the field into having these conversations and being more explicit about the data cleaning that we do and what it ended up removing?
Okay. I don't know if this answers to your question or not, but my sense, how I feel is that at some point, you want to, so there are two processes actually when we do the EEG research. One is to educate ourselves. So we have to expose ourselves to the raw data in the time series, and we have to go through, thousands, tens of thousands of, those epoch rejections, so that we first become the, artificial machine learning device itself, right? So that we are learned. Then we apply our intuition to the algorithm developing and stuff like that. Sometimes I see people from the purely engineering field, and they can, they can use complicated mathematical solutions very fluently, but they have, no intuition in what the data should look like. So they sometimes do something really nonsensical from my viewpoint. So we definitely need the balance between these two. And another thing is that once you get some results from the statistical, you follow the statistics to do the data analysis. And when you look into each data using your intuition and learned eyes, then you find, oh my gosh, this is really bad signal still remaining. And this often happens. But remember, we are psychologically always very biased, and we have a very specific biased way. I have seen many end users saying, oh, but this algorithm doesn't take care of that and that, but they can't show the the statistical evidence of it's not working. So we are always kind of biased by those outlier bad results, and we say, oh, this algorithm doesn't work. But overall, it works. And if someone says it doesn't work, then they have to show some statistical evidence for that. And so, those are probably the things I can say for that.
Linda, you get the last question.
Really great talk. I really enjoyed it. I have a question that's pretty specific, and I admit it comes from apparently ignorance I didn't know I held. So I was aware of the eye-related signal in gamma, but I actually thought it was in the high gamma, and the data you shows it in low gamma as well. I was very interested in that finding. Is your opinion that all gamma-related signal is eye-related in EEG, or what?
I think we can still record the genuine EEG gamma under well-controlled situations. And also careful interpretation and analysis. For example, if we monitor the micro tremor of the eyeballs using the high resolution eye tracking system, then we can significantly reduce the probability of misled by the eye movement or Saccades related gamma. So these are the real practical countermeasure to exclude the possibility of misinterpretations. Right? Otherwise, only by using signal processing, there are things we can do, like using some very smart algorithm can sometimes help, but it's actually better to use those eye trackers, for example, to monitor the eye movement. These are like the ground truth-based processes, so they are always better than just signal processing.
Makoto, thank you very much for your time and for this talk. That was great. We really do appreciate you spending time with us. We've recorded the talk, and it will be available on Confluence. For those of you who don't know what Confluence is, you can email us and we'll be able to send you the link. So thanks very much.
You're welcome.